Appreciate it. All right, guys. Right, so let's see here. So I see about, maybe a third of the class here today, which is good. So hopefully I'll see more on the day of the exam. It's always exciting to see all the students that we didn't know we had. But in any event, let's see here. So you guys have a couple responsibilities this week, right? So your project proposals are due tomorrow. I've gotten emails from, I'd say, about a third to a half of the course worth of students with like ideas about their projects and questions and things. That's great. You don't have to. There's no requirement there. But if you have any questions, you want to run something by me, or like just sanity check, like is this easy or hard? I've taught, this is probably my 7th graphics course, so I've seen it all. So just let me know, and I can give you just a rough idea at least. Yeah, those of you who have found entire PhD theses that you want to implement, that's super cool, but do make sure that you structure your project in a way where there's steps and you can do the steps. Just to trust me, you don't want to be at the last minute implementing an entire thesis just to realize that there's like a bunch of holes in it that you didn't know because it looks kind of polished from the outside. It's a common occurrence, and especially if you're not used to, like, you know, if your SPM or your neural network, whatever, isn't well trained on like looking at an academic paper and quickly figuring out if it's crackpot or not, you can end up in a bad circumstance that way. In any event, that's that. So for your proposals, I think the requirement is what, like a paragraph or something. There's a online submission thing all set up for you guys. And then my goal in the coming week, although I'm realizing I committed to a lot of things, is to send each of you a little bit of feedback, just thumbs up, thumbs down, is this a good idea or not? If I tell you it's not a good idea, you won't lose credit for your proposal. It's perfectly fine. That's why we have a proposal, is to catch these things early rather than having you suffer for the rest of the semester. Any questions about the project? Cool. Oh, one other thing that I'm not sure I've ever actually announced to you guys, which is that every year we judge the project and the best one gets a free trip to SIGGRAPH, which is a big computer graphics conference. For some reason, I never remember to announce that, and it catches the student by surprise. Yeah, so if you're gunning for that, that's cool. If you're not, that's cool too. Plenty of people get A's that aren't going for that. You and then you. Yeah, what's up?
In terms of like, so I saw like the breakdown in terms of like, oh, there's a presentation,
Mm-hmm.
there's a write-up, and there's like, you know, but I was just kind of having discussions with people, and there seems to be like a non-understanding of whether or not like there's emphasis on stuff that's like technically or like back-end difficult behind the scenes, or something that's just like kind of visually appealing, or something that's like.
It should definitely be the first. Yeah, so this is a computer science, computer graphics course. So if you find that you are focusing on the artistic content of your project, you have done something wrong. Yeah, this is a course where you should be implementing algorithms, right? And so what I'm gonna be looking for in your proposals is like, this is what we covered in this class, this is what I'll be implementing on this thing, this is a source I'll be working from. This is an undergrad class, so I don't expect it to be research level. It's perfectly fine to just reproduce something that's already out there. And the rough, you know, it's an open-ended project, but roughly on the order of 2 homeworks is what we're looking for. But it's pretty loose, yeah. But really, artistic content is cool, but unnecessary if you're like spending all your time setting up a 3D scene that's like, doesn't count toward your project. That's just like a thing that you did to demo it. Similarly, if you make a video game, that's cool. Lots of students choose to do that. But if you find yourself focusing on the gameplay or even like the AI in your game, then something has gone wrong. It can be a really boring game. That's fine. That's not the point here. Yeah, does that clarify that one?
Yeah.
Cool, yeah.
What are the expectations for like the project check-in?
I think minimally what we wrote down on the project check-in was that you've written some code and can share a screenshot. So there's some amount of writing that's supposed to go in there, and then a screenshot, even if something isn't working, just something so that we have a visual indicator that you have implemented a graphics technique of some sort and have some signs of intelligence. Yeah. Any other questions about that? Yes?
How do you decide what the best project is?
You follow your heart. Any other questions? Yeah, no, there are many topics in this class, and you should just find what you're most interested in. I wouldn't worry about it. This is intended to be an open-ended thing to pursue your interests. This is an upper-level undergraduate course. There's supposed to be uncertainty here.
Well, I meant is, how do you choose which is the best project to award together, like SIGGRAPH?
Oh, how do we choose the best project, not which one is best for you? Completely at our discretion. That's how. Yeah. Yes?
Oh, is it okay if we use, like, or borrow or get inspired by, like, pieces of code that we've written?
Yeah, you can even use other people's pieces of code, so long as you communicate that beyond this thing that I'm building from, I will be doing this. Yeah. So some people choose to work from tutorials that do like include code inlined. That's where it gets a little dangerous, because if essentially all you're doing is like translating their DirectX to my OpenGL kind of blindly, that's not so great. But if you do that and extend it just a little bit, that's probably sufficient. Yeah. My experience in this class is that the students tend to overshoot. I rarely see a project, at least in its specification, that undershoots the requirement. Yeah. Any other questions about that? Cool. And then the other thing coming up in this course is your exam, which is on Thursday, and will be drafted tonight, whether I like it or not. I promise I'm going to write it any day now. In any event, your TAs have contributed some nice questions, so it's my fault not to finish it off and make sure that it fits together. Let's see, in terms of your exam, as you know, there's one double-sided sheet of notes. Every year, for some reason, somebody asks whether they can have two one-sided sheets of notes. That's fine. I do ask that they're handwritten, unless, I know some people have accommodation about that kind of stuff. If you do, that's okay. The reason why is, like, if you look at the past exams, you'll see that, like, I'm not testing you on a bunch of, like, detailed vocabulary words and the difference between this detail of this method and that detail of that one, right? They're mostly just high-level stuff and calculations that are common in graphics world. So if you find yourself copying all the slides, you're doing something wrong, which is really the point. If you take one of my math classes, then I'll say, like, sure, bring the textbook, bring a friend. In this class, we're not going to be quite that evil, but you know, it's really like, don't bother like memorizing every word, because it's if I think there's like a goofy vocabulary thing that's going to trip you up, I'll just give it to you on the exam. There's no reason for that, right? Like, we're teaching computer graphics is not the kind of discipline where you're going to be like held at gunpoint and asked to ray trace a hyperbolic sheet or whatever. Like, you know, it's mostly worrying about the reasoning rather than the method itself. Yeah. Any questions about the exam? Cool. Okay. Oh, and the last question, which I was anticipating getting, but I didn't, is what does it include? And that is everything through and including today's lecture. Yeah. Okay. So let's do that really fast. So today we're going to talk about shadows. Shadows are also the topic of your last homework in this class. So this will give you all the material you need to finish that guy off. And it's also just a good example of how the ray tracing world that you've already interacted with and this new universe, which is rasterization, are somehow totally different, right? The techniques that we get for shadows and ray tracing were relatively easy to implement, right? Like, it's just a couple extra lines of code inside of the ray trace you already had. What we're going to see is that getting a shadow that can be rendered in real time on your graphics card is somehow like an inner ring of hell, right? Like, sorry, it's much harder than just the basic rasterization task. Like, it's really a big level up that has to happen. So naturally, we're going to make you do it on your homework. Okay, kind of amusingly, this class, and I noticed most other graphics classes spend a lot of time justifying to the students why shadows matter. I personally find this to be a little goofy, but in any event, in case you didn't know, shadows appear in our everyday life, and many times we use shadows as important visual cues in the real world. And of course, I think these slides are around mostly as a historical artifact that it used to be when shadows were so expensive we couldn't render them. We'd spend a lot of time trying to convince ourselves that was okay. But now that we have the capability, somehow we've flipped to the converse. But in any event, shadows really are an important part of a 3D scene, and they tell you a lot about depth, where the lights are, you know, where objects touch each other, and so on, right? Like, you can see in this particular scene, if you remove the shadows, I think it would be really hard to parse what's going on. But given the lighting effect here, it's very easy to understand the 3D relationships between all the objects and so on, which is essentially why we have to spend so much time in our video games writing shadow code, right? And that's really the point here, is that when you're engineering your code for real-time graphics, you have this budget of time, and the way to think about it is that you can spend that budget however you want, right? You've got a 30th of a second to draw whatever you want on the screen, and you could spend it on shadows, you could spend it on reflections and refraction, you could spend it on subsurface scattering or really fancy lighting computation or whatever. Shadows appears to be one of these ones that's really worth that extra computation time because it really does matter in your 3D perception, right? That's the basic point here. And indeed, you can mess with it in assorted ways. Like, here's a guy standing next to an oil splat on the street, and of course, Actually, my brain is kind of weird. If I stand too close to it, it looks like an oil splat, and as I stand farther away, it kind of looks like he's levitating. But in any event, of course, you can manipulate shadows and give false depth cues and contact and so on, right? So here's another nice example. So here, everything about the top and the bottom scenes is identical except for the position of the shadows. And of course, we parse these two 3D scenes very differently, right? Like these guys, it's very clear the spheres are on the ground. Here, it kind of looks like they're levitating. Notice a couple things went wrong, which is kind of interesting perceptually. We're going to start to like nudge our way into perception a little bit toward the end of this course. We'll talk a bit about that kind of stuff. The spheres in these two images are identical. They're just copy-pasted like images. Does that make any sense for the scene on the top? No, right? Because clearly the plane that's sitting underneath the spheres is foreshortened, right? It's getting smaller as it moves farther away. But just by virtue of sticking these little shadow cues underneath this thing, your brain's perfectly happy to ignore the fact that the sizing doesn't really make sense here in favor of a depth cue from the shadow, right? So this is just a nice example that essentially shadows matter for depth, and if they weren't there, I think this scene would be very hard to parse. Does that make sense? I don't think this is totally unreasonable. And indeed, this goes back historically too, right? So if you wanted to create a very realistic painting back in the day, maybe you cast a shadow, of course, with your candlelight, and on the other side could trace an object. Okay, so how do we do shadows and ray tracing? This is worth thinking about for a minute, because of course your exam is coming up. Remember what happens. We send out all our rays from our eyeball into the 3D scene. We hit an object, and we say, is this object lit or not, right? And so the way that we did that is we drew a ray toward the light bulb. And if that ray intersects something else, what does that tell us? Well, it tells us that something else is getting in the way of my lighting, and I shouldn't light it. And otherwise, if I can draw a ray from here to here and hit nothing in between, then I say, aha, I'm getting light. The light is hitting the surface, and I should do the appropriate computation. What goes wrong in ray tracing? Why can't I do that? Or sorry, what goes wrong in rasterization, rather? Yeah, I assume that's what you were going to answer. Nope. Well, remember that rasterization, I'll give you a hint. So one of the advantages of rasterization is that I don't have to keep my whole 3D scene in memory. Remember we talked about this? Like I can do it one triangle at a time. Could I do this shadow algorithm in that case? Yeah.
You won't have in memory any triangles that are between you and the light?
That's exactly right. So if I'm drawing my scene one triangle at a time, I'm not sure why I'm carrying this around, then when I draw that secondary ray, what do I have to do? Well, now I have to intersect that secondary ray with everything in my scene. But I can't because I only got one triangle in memory, right? I threw everything else away. So from the get-go, my sort of shadow method in ray tracing is broken, right? It's not a technique that I can do if I'm streaming one object at a time into my rasterization algorithm. Yeah? Okay.
I feel like it doesn't really do shadows, essentially just like makes some objects invisible, or like black, I guess. Like,
but isn't that what a shadow is?
but like, if there's a ball and a light going on it,
Yeah.
you're not really getting the shadow behind it, you would just get like if there's something in between.
I suppose Aramis has a bit of a philosophical point here. I would call a shadow the lack of light rather than a thing that you render. In which case, I would argue personally that this is doing exactly the right thing, which is checking if that light is obscured. I don't know. I'm gonna have to think about that one. I'm not sure it matters procedurally, but I don't know. But it's certainly going to be the case when we talk about rasterization. We're actually, especially when we talk about shadow volumes, we are going to render our shadows, which is kind of a weird thing to think about, and something that I always struggle to communicate in lecture. So we'll see how well we do today. So we'll come back to that one. I'm not totally sure. Any other questions I can fudge my way out of? Fabulous. Okay, so today, this is again a little bit of a shorter lecture. I guess we have a few of these kind of glued together. I keep saying that and then going over time. In any event, we're gonna talk about two key strategies out there for rendering shadows in the rasterization world that makes sense if you just have this sledgehammer that knows how to draw triangles, right? Your GPU. That's all it knows how to do in life. The first one is the one that you'll implement on your homework. This is a technique called shadow maps. And inside of shadow maps, there are sort of things you can do, like percentage cluster filtering is a strategy for anti-aliasing your shadow maps, which we're going to see is a big issue with shadow maps. And the second one we'll talk about is something called shadow volumes, which are super cool and were popular for about 10 years, somewhere between like 1998 and 2008, and occasionally show up in video games, but we're going to see that they're quite expensive in practice. So very rarely do they show up anymore, which is too bad, because they're cool mathematically. Okay, and of course shadow maps are really critical. So basically anytime now, if you look at if you look at 3D renderings, especially in video games and in films that aren't ray traced, essentially a very large piece of your computational pipeline is being devoted to this stuff with remarkably high success. I mean, here, this is from EA from a couple years back. You can see that the shadow here is very high resolution. It's being cast on the scene. They can move the light around, and that's no big deal. And this really is a fairly recent development because it's not totally obvious how to render shadows in the rasterization, one triangle at a time setup that we currently have. Yeah, I mean, we don't even, we're like building up the Z buffer as we go along. We don't even have an accurate notion of depth necessarily when we draw one triangle. Yeah. Okay, so shadow maps, the basic idea here, I think actually, hopefully you guys recognize this animation, right? It's called Luxo Jr. It was one of the first Pixar shorts. The cute lamps, they hop around. There's good Halloween costumes every year that kind of look like these. I was going to this year, and then Moon told me that wouldn't be cool as a professor if I dressed up. So blame her. In any event, right, so what we're going to do, obviously in a movie like this, shadow maps were really critical. I mean, it's a film about lamps. Yeah, and indeed, this was one of the early examples where shadow maps were used. And I believe if you look really closely, you can actually see some of the artifacts. But anyway, essentially the point of shadow maps is that you're going to render your scene from the perspective of the light bulb. That's what you're seeing down here. Just the depth map. You're not going to worry, the Z buffer. You're not going to worry about the color because that's not going to matter necessarily, at least for the kind of version 0. And then you're going to use that to render your shadows from the perspective of the camera. So we're going to go into some details there. But essentially, what the basic point here is that when I render the scene from the perspective of my light bulb, what am I doing? What is the Z buffer kind of telling me? It's telling me how far the light ray travels before it runs into something, right? And that's going to be a useful piece of information when I render the scene from this perspective of the eyeball. This is also our very first example of sort of multi-pass rendering is a key phrase here. And that just means, like, how am I going to do this? Well, I'm going to iterate over all the objects in my scene twice, right? Once to render the scene from this perspective of the light bulb, and then a second time to render it from the perspective of the camera, right? So it's a multi-pass technique. Okay, so here's the kind of duality that we're working from, which is that somehow there's a duality between figuring out what's visible from your camera and figuring out what gets lit, right? So in particular, if I think of my eyeball as kind of like a flashlight, right? And I shine my flashlight onto all of you guys, what's going to happen is the thing that receives the light from my eyeball, it's going to be a very weird universe, is exactly what's visible. Do you see that? Because both of them just involve drawing straight lines until you hit something. And so that's the duality that we're basically leveraging here. We already wrote a piece of code that does the second thing, and we're lazy programmers, so we're going to see if we can reuse it for the first thing. Okay. And so that's the basic point, is that a point is illuminated if and only if it is visible from the light source. We're really good at visibility using Z buffering, and so we're just going to reuse that technique. Okay, so let's do a little bit more detail. This is one of these calculations that's easy in concept. I feel like I say that a lot in this class. Like, it's easy conceptually and also easy to get wrong while you're coding it, which is why it's on your homework. Okay, so right, so here's what I'm going to do. So I'm going to make a new object, which is another buffer. Remember that buffer is a term for like a little piece of memory on my graphics card that stores an image. I'm going to make a depth buffer for my light bulb, and I'm going to render my scene from his perspective, right? So essentially, the shadow map is just the depth from the light source, or 1 over the depth, or whatever. It really doesn't matter, right? But I'm going to just reuse the rendering tools that we already developed in our last lectures. to draw the scene from the light bulb's perspective. So I get some object that looks like this. So hopefully you guys can kind of parse images that looks like this by now, right? This is a Z buffer, so notice that, like, for instance, the table is getting farther away from the light bulb, which is why it looks lighter back here, darker here. And so that's the thing that I get in my initial pass. And now I'm going to do kind of a funny calculation, which is now I'm going to render the scene from the perspective of my eye, right? So maybe I'll draw a picture. Let's see if we can manage to get this right. So there's the ground. Like maybe here's an object, here's my light bulb, right? So here's my shadow that it's casting, right? Okay, so now I have my eyeball, and he or she is looking at the scene from this point here, and now I'm rasterizing my shape, right? So what can I do? Well, as I rasterize my scene, maybe I find some point here on the surface that I'm trying to render. I'm drawing this like I'm ray tracing, but really I rasterize. Like I found this point and then maybe I drew that line later. Okay? How can I figure out if it's lit? I'll give you a hint. I'm going to draw this line from this point to the light bulb. And I can compute its length. All right? Yeah. That's exactly right. So the shadow map, remember, it's like a little image kind of sitting here. It's telling me the depth from the light bulb where the light hits. So what am I going to do? Well, I can figure out what pixel I'm at by intersecting this line from the point on the surface to the light bulb. I intersect that with the depth map to tell me what pixel I should look into. That's okay. That's a SIMD kind of calculation. Now I read off that value in the shadow map, right? And that tells me that in this pixel, my light hits some object that's this distance away. And now I compare that distance to the distance of the object that I'm rendering and the light bulb. And if that distance is larger, well, then it doesn't get lit. And if it's smaller, then there's something wrong in the universe. If they're equal, then it does. Does that make sense? What are some problems with this technique? Let's maybe anticipate them a bit before I go over them. Yeah.
I think we'll probably have to throw in an epsilon cryptic.
That's right. So any time that you have double precision values, if you're checking that they're equal to one another, you have done something wrong. I have a bumper sticker that says that. It's a very long bumper sticker. That's absolutely right. Any other issues? Yeah?
I mean, does the, if it's a point light versus a spotlight one, that should matter how we trace the ray?
That's absolutely right. So far I've only kind of described this for a point light. We've got to figure out what to do when we have lights that are other shapes. Yeah?
Global illumination?
Global illumination, which is pretty much a no-go in this scenario. There's another big one. So let's take a look. Let's say that I took an even grid on my screen here. And I look at where the center of each one of these pixels ends up. There's a projection onto the ground, right? So now I'm going to get something like that, right? Like I take the image grid from my light bulb and I just project it onto the floor. I've tried to draw this very suggestively. Yeah.
The angle makes it so the pixel space isn't equivalent to the actual space in the real world.
That's absolutely right. Like this pixel is somehow accounting for much more of my scene than the one on the bottom of the light bulb. In other words, I'm likely to run into what issue? Starts with an A and ends with Aliasing. Thank you. Yeah. This is a great source of aliasing in video games, right? Because it's very hard to choose a resolution here where I have a nice even grid for my shadow map, but that's not really what I want. I would like it to be even with respect to the perspective of the floor, but I don't know that when I draw my shadow map. In fact, if I'm moving my light around, I can't control for that. You know? So these are all going to be problems. Okay. Right. So anyway, the shadow map computation conceptually it makes a lot of sense, right? Essentially, I'm just comparing, the distance from the light to the thing the light runs into relative to the distance from the point that my eye sees relative to the light, and seeing if those are equal or if one is bigger than the other. Right, and that's essentially what's going on. Yeah?
How do you go from a point in the scene
Okay. Yeah, so there's a bunch of geometry that has to happen in this homework, and this is one of the things that you'll work out in detail in your homework. But essentially, right, there's a few annoying things you have to do. One is compute the distance from the point that you see to the light bulb. That's okay because your light bulb is just a constant global variable, right? So it's just distance from that point you just rasterized to this point in 3D that is just fixed. So the larger issue is how to figure out where you are on this grid. But the thing is, I actually know the camera projection for the shadow map, right? So this is a point in 3D. And remember, how do I figure out where points are on the image grid? Well, I multiply them by the camera projection matrix, right? So what I'm going to do is compute this 3D point. And normally I would project it onto the eyeball camera. But instead, I'm going to multiply it by the light bulb's camera projection matrix. And that's going to tell me where to look in this grid. Yeah. Again, all details that are easily gotten incorrect in your code. So be careful. Yeah. Any other questions? I know this is one of these ones where there's like a lot of juggling going on and it's hard to remember all the different pieces that go into it. Maybe we'll look in a little more detail. It's also written out on the slide here. So again, right, you kind of compare your depth value. That's what's going on here. Okay, and so, right, and of course the projection is the really key step, which is figuring out how you go from this point in 3D into the point in the shadow buffer, which you just computed. And the way that you do that is that essentially this is nothing more than another camera projection matrix, just with respect to some other image grid somewhere else in the 3D world. Now to return to Colton's point, one thing that we didn't do was talk about different light bulbs. And indeed, that's a really critical issue, right? So here's 3 different examples. So one of them is a spotlight, one's a directional light, one's a point light. And each of these, unfortunately for us, requires a slightly different computation. Yeah. So in particular, the scenario that I've drawn for you guys on the screen, right? There's like a little image grid here. What happens outside of this grid? Like, can the light cast rays that are outside of this little screen door I've put in front of it? Not really, right? I don't have any information. Like, I don't have a depth value to compare there. So I probably would just not light points. So in other words, this light bulb, you can think of kind of like a spotlight with a square. What do you call the thing on the side of a spotlight that's limiting the direction where it can go? I have no idea. Shade? Sure. It's like a square shade around a spotlight, right? Because that's where the shade sides are kind of defined by the image grid. If I wanted a directional light, so just like a square worth of light, that'd be pretty easy to do, right? We could use our orthographic camera projection. If you don't remember what that is, might I suggest a bit of review before your exam. Actually, the trickiest one, which the kind of funny thing is the easiest lighting to do in ray tracing is a point light, right? Because the basic issue here is, if I really wanted a point light that could cast light in any direction, what would I have to do? I'd have to kind of put these shadow maps everywhere around my light bulb, right? Because otherwise I don't have that depth test to compare against. That's hard to do, right? This is only covering kind of one side. And so a very typical thing to do might be to put a little cube around your light bulb. So now you kind of think of your point light as really the union of 6 of these spotlights kind of glued together. If you think about it, that can create some really bizarre aliasing, right? Because what it means is that there's somehow a set of cube edges around your light bulb that's going to get less resolution maybe than right in the center of each of the faces. The reality is actually there are very few point lights in real life, right? In fact, I don't think I see any around us. So it just doesn't get used all that often. Any questions so far? Cool. High energy classroom here.
Sorry.
Right, yeah, there you go.
Exactly, are we doing the cube thing again?
Sure. So in the cube thing is for a point light. So a point light casts light everywhere, right? It casts light up, down, left, right, and so on. The problem with the camera projection is that it needs a side, right? I need to put an image plane in front of me. There's no single image plane that wraps all the way around your light bulb, right? And so the way that we get around that is instead of thinking of there being one light bulb casting light everywhere, we think of there being 6 light bulbs that cast light up, down, left, right, forward, backward. Yeah.
End up covering everything.
Exactly.
Okay.
Yeah, great question. Any others? Cool. Right, so yeah, so here's what this looks like. For example, for the directional light, is that you end up with just an orthographic projection matrix. In fact, your code conveniently calls it an orthographic projection. Remember one thing that we talked about last lecture, maybe 2 lectures ago, was this idea of having a clipping plane, right? That like if something is more than some distance away or less than some distance away than my camera, those are 2 different bounds, then I don't draw it, right? And that way I can kind of limit the precision that I need in my depth buffer. What that means is that our shadows are kind of super weird, right? Anything outside of this cube doesn't receive light, which is not particularly physical, but that's just the kind of limits of the engineering that we have. In any event, so in this particular scene, there's what the depth image looks like, which I think we've seen a few different examples of so far. Right, so the way to do this is now as I'm rendering my 3D object, maybe I have my, a matrix which takes me into the coordinates of the light bulb, and then another one which is the orthographic projection going from the 3D coordinates of the light bulb into the light bulb's image plane. Okay? And then NDC, I think, is a term that we haven't used a ton in this class. Anybody remember what this stands for? I remember it came up once. This is the... That's exactly right. Normalized device coordinates, which is a fancy phrase for like, it's really convenient to have numbers between -1 and 1. So that's what's going on here, is that I might as well think of my light bulb's little image screen as just being in the unit box. Yeah. So here's what our code might look like with lots of ... dots in it, because that's your homework. Right, so here, one thing that we're gonna have to do a lot is the set frame buffer business, which is telling me I've got all these different buffers in my screen, which are all the different sort of canvases that I can paint on, right? So the very first thing I'm gonna do is say, first I'm gonna draw into the depth buffer, now do some stuff. Now I'm gonna draw into, my default, like my screen thing, and then do, actually draw the scene, right? So when I start writing into the depth buffer, in this case, by the way, I need a different depth buffer for each light bulb, right? So there's a limit on the number of lights that I can have. Now I draw my current thing, and I move on. We have to be a little bit careful. So for instance, there's one really, really annoying convention in almost all computer graphics software that trips people up. I believe that this is the case in your homework. Your normalized device coordinates are between -1 and 1. Your texture map, because it's stored in a 2D array on your computer's memory, is usually between 0 and 1. So just FYI, there's a little bit of a scaling that has to happen. So if you end up seeing, for example, half of your shadow and it looks 2 times as big, probably that's what went wrong. This is a stupid thing, but you would be surprised how many times I've seen it go wrong. And then finally, right, so here's our pseudocode so far. Right, so maybe you write, normalized device coordinates to texture coordinates, which probably multiplies by 2 and adds 1 or something like that. Divides by 2, I guess. In any event. Now I have this comparison, right? This is checking, am I in the shadow or not? This is the critical less than sign. What's wrong here? Well, for one, it should at least be, exactly. So you need a little bit of wiggle room in this computation. And in fact, this is really a nightmare to set properly, because essentially the resolution, again, depends on where you are in the shadow map. And so oftentimes what you'll get is if your epsilon's too small, you'll get noise. If it's too big, you'll do something crazy, like cut off your shadow at a random arbitrary point. So here's what this looks like, which is, instead of epsilon, for whatever reason, oftentimes people call this biasing, because that makes them sleep better at night. This artifact here is sometimes called self-shadowing, right? So what's happening is you're hitting this surface, this guy, which really does get lit, right? So light bulb is like somewhere here-ish, right? So I compute this distance, and it's roughly equal to the distance that I think it should be, right? Which means I should light it. But like because of noise, those numbers are slightly different. And if my tolerance is too small, then essentially there's just noise happening here. And every once in a while it's saying it's shadowed, every once in a while it's not, right? This is because my epsilon was too small. So now I make my epsilon bigger. For a while I'm happy. And then what can happen here? Well, if this is shadowing too often, if I make epsilon too big, what's going to happen? Now I'm not going to shadow enough, right? And indeed, if you look at your shadow, notice there's a little bite out of it in the bottom corner. This is obviously exaggerated. I don't think anybody would choose an epsilon that's like this distance here. But essentially what it's saying is that if this amount of space is between the lit thing and the thing that might be in the shadow, I'm going to call it lit. right? So anyway, this is a number that's very hard to choose correctly, and that's just sort of life in this particular area. That's why often if you look at video game shadows, you'll see lots of aliasing. It's just hard to do this stuff correctly. Yeah?
It looks like it's happening in the correct image a little bit.
Yeah, that's because your instructor is bad at writing code. Yeah, you're right. There's a tiny bit of artifact right here. Or maybe that cube is hovering slightly over the ground. There's really no way of telling. Okay, yeah.
Why is the noise kind of like stratified?
It's a good question, right? The noise somehow has to do with the y coordinate here. I don't know. Yeah, probably something to do with rounding, right? Like you're seeing integers or like you're seeing the spacing between double precision. It's hard to say. Yeah. But essentially, it's undesirable. That much we know. Yeah. Any other questions? Yes, Kawa. Why is the right side of the cube not... Anybody have a good answer? Why isn't the right side of the... Why is it not lit? Where's the light bulb here? It's probably like kind of up and to the left. So what do we know about the normal of the cube relative to the direction of the light? Yeah, so the whole side of the cube is just facing away from the light bulb, so you can very safely not light that. Yeah. I mean, you can, but it's like... This is in a shadow for two different reasons, right? One is that it is facing away from the light. The other is that it's also occluded by the other side of the cube. You can choose your poison here. Yeah. Yeah. Any others? You guys are picky today. Cool. Right. So let's continue. Yeah.
Also, like the ceiling of the cube in the middle one is also just slightly darker. Is it like that whole thing got?
Yeah, I think that whole thing shadowed itself. Yeah.
From the Z fighting?
Yeah, exactly. Oh, incidentally, apparently we've heard this term before. Another term for this noise is called Z fighting, right? Which is that somehow there's two things that are fighting to be on top because your epsilon's too small. Yeah. Any other questions? These are all great questions. Cool. Okay. Let's talk about some things that can go wrong in case we haven't seen enough of those. Here's another one, which is aliasing. So here's our favorite levitating teapot 3D scene. And now I'm going to choose to light it two different ways. One is the sort of boring top-down, interrogation style teapot lighting. And the other is a more dramatic kind of sideways teapot light. So, on the left-hand side, we're seeing one of those. On the right-hand side, we're seeing the other. What do we see here is that, like, this entire region in my rendered image is probably very few pixels in my shadow map. In fact, you can see the pixels in the shadow map in this image, right? Yes? Nods? Something? Are you guys alive? Yes. Okay, good. And, right, so essentially, this is an aliasing artifact, and there's two different ways that you can undersample, right? One is just by, the usual aliasing problem. I'm just making one sample per pixel. But now I have a new set of things that can be undersampled in the shadow map, right? And both of those are working together to create just an awful image all the way around. How could I fix this problem? Yeah. Sure, so what should I oversample? Should it be, like, should I somehow anti-alias from the shadow map?
I guess if there's like a grid, like if you have the grid, then you can just make the grid more fine, I guess.
Sure, so one solution to my aliasing is sample more, but maybe I have a limited amount of memory on my GPU. I can't make it any denser. What's a person to do? Interpolation. Okay, so in other words, when I do my shadow lookup, I mean, clearly here, when I did my shadow lookup, I just rounded to the closest pixel, right? I could try and interpolate. So let's go back to our picture here, and let's do that. So let's say that I have two pixels next to each other, and one of them goes onto my 3D object, right? He's here, and now I draw the next one, and goes onto the ground, right? That's our basic source of aliasing here. What would happen if I interpolated between the depths of these two guys? I'd get some point like there-ish, right? So it's actually not clear that interpolation makes a whole lot of sense for shadow mapping. In fact, it really wouldn't, right? Because what it's doing is sort of taking 3D objects and then smoothing their geometry out. So actually the typical thing to do in shadow mapping is not to interpolate at all. You just round to the closest pixel and use that guy's yes or no shadow computation for exactly this issue, which is otherwise you're hallucinating points in 3D. So essentially my point here is that it's actually not so easy to anti-alias because there's aliasing in your shadow map, which is hard to remove. Because if you just smooth it out, you end up with like a 3D structure that isn't there. And so there's a bit of a trick, which is typically what we use, which is to say, well, we can't really filter our shadow map directly. Do you guys remember we had a rendering trick, what, 1 or 2 lectures ago, where we did our lighting computation once, but we did our occlusion computations a bunch of times? Like we had a bunch of, I always forget this, so there's super sampling and multi-sampling, right? This is a little bit of exam review. So remember in multi-sampling, I do like, which triangle am I in a bunch of times, but then I only do 1 color per triangle or something like that. That was already enough to get a pretty good anti-aliasing effect. We can do a similar thing here for shadow maps, which is to say, I really do need to round to the closest pixel in my shadow map. Interpolating doesn't make a whole lot of sense. But what I can do is multi-sample. I can draw a bunch of samples in the interior of my pixel and do that shadow test, which is rounding a bunch of different times, but drawing slightly different lines. So in other words, I'm going to anti-alias over here, but still use the same alias computation over there. That makes some sense? So that binary thumbs up, thumbs down decision in terms of am I in a shadow or not still has that kind of jagged edge, but it has a jagged edge in the image plane. At the very least I can do is blur it out if that jagged edge occurs in the interior of a pixel. Yeah, that's what's going on here. And so here's a nice result. So this is called percentage closer filtering, right? Because it's like the percentage of pixels that are closer to the light than the you know, whatever's in the shadow map. And it actually gets a nice anti-alias shadow only right around the boundary of the shape. There's kind of a happy coincidence that happens in this particular technique. Notice that the side of the shadow looks kind of fuzzy. Is that, like, should it? like, do I have an area light? No, this is probably still a point light source. And the only reason it's fuzzy is because I'm anti-aliasing in the shadow map. But that's sort of okay, right? Because most light sources have soft edges anyway, right? And so this is sort of just a lucky break that somehow this technique that we use to anti-alias our shadow map also creates shadows that probably would be hard to do otherwise. On the other hand, getting like a really, really sharp shadow edge would be quite hard to do. That's what creates aliasing. So like these interrogation scenes where like I hold a light bulb right up to you and you know, there's some very dramatic thing going on. That's what's hard to capture. But these like nice softly lit outdoor scenes are much easier. Any questions about that? So the trick is to, again, to super sample the computation of am I in the shadow or not, but that computation itself is going to do some rounding. Yeah. Yes?
So is, can I just make a question? So is the name of this technique the percentage closer filtering?
Yeah.
Okay.
Because it's kind of like the percentage of the pixel that is closer, you know, to the light than whatever the depth buffer is saying. Something like that. I don't know. It's a historical term. Oh, because you're not actually doing any kind of anti-alias. You're not actually doing any kind of soft lighting, right? Like this is just a way to deal with low resolution in your shadow map. So really, this is just a.
The blur is happening in the middle too, but you don't notice it because all the colors are the same?
Not quite. So the blur here is just because this is sort of the projection of one pixel in your shadow map onto your 3D scene. Right, so that's the reason you're getting the blurriness. It has nothing to do with the soft light.
Yeah.
So like over here, it's completely dark because the entire pixel is occluded. Yeah. All right, so that's the basic trick here. Really, really clever idea. Yeah. Of course, the other solution which we propose over here is like, okay, if you're not getting enough detail, then maybe, you know, add more pixels, and that's actually a reasonable solution. Here's the basic point of why this can go wrong. So here, what we've done, here's a 3D scene. There's a shipwreck in the corner because why not? And here's the shadow map where we've taken the grid of pixels in the shadow map and just kind of projected it onto the ground. So every one of these green regions is like one pixel. And what do you notice? Well, they're just non-uniform in size, right? But the size of the square here, really annoyingly, is not just a function of the light bulb. In particular, let's say I have my 3D character, and now he walks over here, and he looks in the other direction. What's going to happen to the size of the green boxes? They're going to flip, right? Like these small boxes, if he's standing over here, are now a big part of his eye, and these boxes become small, right? It just depends on, it's all a matter of perspective, if you think about it. Yeah? So what does that mean? If you want to do these kinds of adaptive techniques where you say like, okay, I'm going to add resolution to my shadow map. Well, what are my options? Either just get a bigger shadow map everywhere, but that's going to be really hard because it's extremely non-uniform, right? So like the amount of additional shadow map I'm going to need over here to get nice resolution is quite different from like already in the back. It's probably okay, right? So instead, there's a clever trick, which is called cascaded shadow maps, which says, I'm going to take the scene from the perspective of the eyeball. This is going to get all kinds of confusing. I'm first going to look at the depth map from your eyeball, and I'm going to use that to guess where I need resolution in my shadow map from the light's perspective. Then I'm going to compute a bunch of shadow maps from the light perspective, and then I'm going to re-render the scene again from my eyeball and use the shadow maps in the third pass rather. Yep. So the basic idea here is that I need different shadow maps in different places with different resolutions. But getting this method right is really difficult because essentially the place where you place this density has to do with two things. One is the location of the light, and the other is the location of the eyeball, and you have to work that out very carefully. So this is not a technique that we're going to cover in this course, but it is worth knowing that it's out there. This was proposed in 2013, so really not that long ago. And if you want really, really detailed shadows in your video game, that's how you can pull it off. So in case you're curious, like this is what it looks like. So the color here, I think each one of these corresponds to a different level in that shadow map. So you can see that like they're roughly sorted by distance to the camera, which is a difficult thing to pull off. In fact, everything about this is really hard to pull off. So for instance, remember we talked about mip mapping? There's this issue that like, as you move farther away from the camera, at some point you flip to the next mip map and there's like a discontinuity in your animation. There's exactly the same problem here, where like suddenly, you know, shadows that pass from the green region to the blue suddenly become like blockier or something. So what you have to do is like all kinds of anti-aliasing and deblurring to get it absolutely right. So you get state-of-the-art quality, but to really pull it off, you have to do all kinds of clever like percentage closer filtering with respect to each one of these regions, and then a second time to combine them all together, which is just really nasty to code. And in addition to that, uses up a lot of CPU time, so it better be worth it. Like your other option is to go talk to your artist and tell them like, hey dude, like just reduce the number of light bulbs. And that's probably a pretty reasonable answer here. Of course, it's getting harder and harder to do. These artists are they're a tough audience. All right, any questions about the high-level idea here? This is not one where you should expect to have to pull off the details. If you wanted a really hard course project, you could try and do this. Yeah?
Is the reason it's like discrete sections to optimize the GPU performance? Because it's discrete.
Yeah, you have no choice. The only thing your graphics card knows how to do is draw stuff on a grid. Yeah, so essentially all of these algorithms are built on top of that. I suppose you could get really fancy. Maybe you could make yourself a graphics card that like knew how to render on a hexahedral grid of some sort or whatever, but no hardware that I know of knows how to rasterize that way. That'd be pretty fun. Yeah. Let's make a weird computer screen while you're at it. Yeah, so anyway, the slides have all kinds of links to this stuff. I think there's even some hardware that can support this stuff, but it's really advanced, tricky stuff. Okay, the more interesting topic is the sort of other school of shadows in GPU world. Well, two of many, but there's sort of two principal techniques. The first is shadow maps, which I think is by far the most popular method. The second one is something called a shadow volume, which is going to use an object called the stencil buffer on your graphics card. By the way, all these buffers have different names, right? Shadow buffer, stencil buffer, double buffer, so on. It used to be in OpenGL that these were actually special buffers on your graphics card. These days, since we have this very general purpose graphics card, that's no longer the case. They're just, you just say, I want a stencil buffer, and now I reserve this many bytes worth of memory, and I have one. You know, there's no distinguishing that happens. And then we'll spend our last couple minutes talking about deep shadow maps, which have nothing to do with deep learning, in case you're wondering. Okay, so shadow volumes is, I can never decide whether this is a smart idea or a brain dead one, but it's definitely one of the two. It's kind of a clever trick, and it makes beautifully detailed shadows at the cost of stupid amounts of CPU time. But for scenes where the object that is doing the shadow casting is not terribly complicated, you can use shadow volumes, and it basically just obliterates aliasing in your shadow map, which is pretty cool. On the other hand, it's expensive and hard to code, and nobody actually does this. So that's your trade-off. Okay, so here's what a shadow volume is as a piece of geometry. Let's say that I'm rendering this square. Here he is, he's blue. Typically, I think about this region, which is the region that gets lit by my light bulb. In a shadow volume, I'm going to do the opposite, which is to say everything underneath this square doesn't get lit. Yeah? And I'm going to do something kind of funny, which is I'm going to cut it off at some point. Like maybe I know the distance of the light bulb to the ground, and so like below that it really doesn't matter. Like I'm never going to see an object there. Yeah? So now, what am I going to do? I'm going to construct a six-sided object, 1, 2, 3, 4, 5, 6, which is all of the stuff which is occluded by this square. Does that make sense? And the really crazy thing about shadow volumes, actually, by the way, it's typically not a square, it's just a triangle. There's obviously no reason to do a square. I'm actually going to make this object as a mesh. Like I'm going to actually make a little volume, which corresponds to this square. It's a constant multiple in terms of memory, right? I mean, this is 6 times what I had before. Yeah? Right, so what am I going to do? Well, as I'm rendering my 3D scene, you know, here I'm rendering a triangle. Well, now I'm going to look inside of, and here's a point on my triangle. I'm going to look inside of every one of my shadow volumes. And what am I going to say? I'm going to say, if this point is inside any of the shadow volumes, it could be inside more than one, right? It could be there's another rectangle sitting on top of this guy. Then I shouldn't light it, and otherwise I should. Notice this is kind of backward from the way we talked about shadow maps, where the default was not to light something. Now the default is to light something unless you are inside of a shadow volume. That make sense? So the naive implementation of this thing is quite expensive, right? So essentially, what would I have to do? For every point here, I'd have to iterate over all of the polygons that could possibly occlude me and all of the possible lights and check each one for each pair of those whether I'm inside the corresponding shadow volume. And moreover, I'd have to construct it to be big enough to include anything interesting in my scene. But I could do it. And that's the question. You know, we can, but should we? Okay, but anyway, this is our basic technique. But now we're going to use a really sneaky trick. It's a really cool idea, which is kind of suggested in this picture. I had a really hard time drawing this. I'm sorry, it's very hard. Let's think like we're ray tracing for a second. We're not actually ray tracing, but just bear with me. And let's follow a ray from my eye to 2 different points. One is on a triangle inside the shadow volume. The other is in a triangle outside the shadow volume. Cool? And here's what I'm going to do. I'm going to keep a binary number. And every time I run into a wall, I'm going to flip that binary number. This is true. I do this, you know. There's a glass door outside of my office. Anyway, right, so I'm going to draw a line from my eyeball to this triangle. And here I'm going to add 1, right? My binary value flips up. Now I'm going to hit another wall. I'm going to flip my binary number down. So what is it now? Good work. And so when I hit this triangle, what value do I get? 0. And it should be, this triangle is lit, yeah? Similarly, I run into this shadow map. It increments, it goes to 1. And then I hit this surface. Should I light this thing? No. Notice that there's a 1 inside of my value when I did that. Yeah? And so there's kind of a funny thing that happens. Every time I hit a wall, if I enter into the volume, maybe I'm going to increment by 1. And when I exit, I'm going to decrement by 1. So what happens if I entered and exited the same number of times, then I am outside of the shadow volume. Otherwise, I'm inside. Yeah? So here's the really clever trick in shadow volumes. I'm going to actually mesh this shape. And I'm going to rasterize it from the perspective of my eye. And every time I have a polygon that faces my eye, I'm going to increment all the pixels by 1. And every time I have a polygon that faces away from my eye, I'm going to decrement all the pixels by 1. And any pixel that's left with a 0, I should light. And any pixel that's left with any other number, I shouldn't. And all of this happens in your eyeball coordinates, right? And it does that by actually literally computing a triangle mesh of the shadow volume and rendering that thing one triangle at a time. It's really crazy that you do that, right? And this is a really clever trick because essentially it's just leveraging the fact that your GPU is really good at drawing triangles. So now I'm still going to just scan line, fill in that triangle, but rather than along the scan line and doing lighting calculation, I'm just going to look in the stencil buffer, which is just a buffer where I'm keeping that number. I'm just going to add or subtract 1 depending on the normal of that triangle. Does the basic technique make sense? Really tricky stuff. So the nice thing is this can make beautifully detailed shadows, right? Because this thing doesn't care about the size of the object doing the occlusion, right? There's no longer like a little grid sitting in front of your light bulb. It's actually the resolution of the things doing the occlusion. And the only problem is, of course, well, you have to render every object in your scene times, what, 4, because now each one of them makes some giant tetrahedron inside of 3D. Well, times more than 4. Times some big number that I don't feel like thinking about. One useful vocabulary word, which shows up in this particular area, is something called the stencil buffer. This is nothing more than just like a useful buffer that I'm not going to draw, right? That's what stencil buffer means. And so essentially the way you can think about that is like, remember this thing, we're incrementing and decrementing those values. At the end, I'm just going to get some binary mask, which tells me this pixel is lit, this one's not, right? And that's what your stencil buffer is telling you. I'm not sure that's worth like going through all these details here. And that's basically it. So essentially, as I render my 3D scene, I look inside of my, so now in my very last pass, I'm going to actually render the 3D objects in my scene, right? And I'm going to look up in my stencil buffer and I'll just like see a 2 here. Well, what does that mean? That means that there's 2 different shadow volumes that are getting in the way of this point, which means I should not light it. And similarly, at this pixel, I get a 0, so I should, right? And so it's just an additional lookup that happens in my stencil buffer. Yeah? Oh, that's just the thing doing the occlusion. So for literally every triangle in my scene, that'll be the top of one pyramid. Yeah. So notice that like shadow volumes could be totally obscured by other shadow volumes like this pair here. That doesn't matter. All we need to do is figure out that one thing covers up my light and then I'm done, right? Notice this suggests a really obvious way to accelerate my shadow volume, right? Like, do I ever need this one? No, right? Because this guy already is doing all the occlusion, so maybe I can throw him away. Yeah. So it's a clever trick. Again, hard to implement, extremely expensive, but super clever and gets really beautiful shadows. So for like very specific scenes where you have like some object with a very dramatic shadow that you care about, this would be the kind of technique you would need. There's some details that are detailed in the slide. I don't think they're worth covering because it's the kind of thing that like inevitably if you code up this technique, you're going to have to wrap your brain around and really worry about, which is what do you do if your eyeball is itself inside of a shadow? There are a lot of different solutions here. Probably the simplest one is throw away objects that can cast shadows until you find the one that contains your eyeball, which I believe is what most people do. Or you could try and do something more clever, like take the shadow volumes and like clip your eye out of them somehow or something like that. But these are complicated details that I could tell you them all today and it won't make it any easier when you code it. Like you'll still have to think through it. Okay, so there's a lot of ways to make shadow volumes faster. Obviously this is a very slow algorithm because it requires rendering giant multiple times the number of triangles in your scene. A very typical one is to notice that, like, for instance, this tree doesn't really need to produce any shadow volumes because it's completely obscured by the house, right? And so a very simple thing you could do would be, like, maybe you have a very complicated 3D scene, but it's fixed, the light bulb's not gonna move. So like, when my artist models the scene, I can now hit some green button and let my computer do a ton of computation to compute that shadow volume once, and then just keep it around, instead of doing it, you know, on the fly for every single triangle in my scene, which can be a lot faster, right? Like in this case, the complexity would be like the complexity of the side of the house, rather than the side of the house, the side of this house, that tree, and so on, because just ahead of time I did some fancy geometry to determine that this tree is completely obscured by this house. That would be hard to do on the fly, but if everything about your scene is fixed ahead of time, you can do that sort of thing. And so anyway, these are sort of passé. People don't really use these anymore. Like they were extremely trendy for a while because you get really beautiful shadows like underneath this horrifying object here. You can see basically all of his geometry. But it's extremely expensive to render this thing. And the reason that it's so expensive is for objects like this guy. Remember that there's a shadow volume that is produced for every single triangle in my scene. Yeah, so this actually is not terribly expensive to render. Your GPU can probably do it, but in order to do shadow volumes, you would additionally to that have to worry about the shadowing that happens for every single leaf in your tree, which is a very complicated object, right? So the term for this is overdraw. In other words, like essentially you're doing tons and tons of calculation just to figure out whether each pixel is inside of a shadow or not. And the reason is that you're like visiting a bunch of pixels to increment and decrement that shadow buffer a bunch of times before you even get to drawing the scene. And especially like on your cell phone's GPU, there's just like no way that you're gonna get this to work this year. I don't know, in like 2 years when your iPhone has like 8 cameras on it, maybe it'll be a different story. Any questions about shadow volumes? It's kind of a cool idea, right? It's like really clever. It's like rasterizing virtual objects that aren't there to help you figure out whether you're in a shadow or not. Okay, so those are the main strategies, and there's many other reading you can do on these kinds of things. There are entire textbooks on real-time shadowing. This is a advanced, difficult topic, and one for which there is not consensus in the graphics community on how to do it. And as you can see, these are just techniques that they're all approximations and hacks in different ways, and for different styles of scenes, you might need one or the other. Right? Like typically, when you're working on a video game, there's like the beautiful graphics theory part where you work on your game engine and it renders everything. You don't have to worry about this. And then there will be like the 3 scenes in your game that the artist is really insistent on that like just don't work with whatever algorithms you've implemented. And now you need some completely different pipeline to render those 3. And that's just life in this industry. And so often you'll have to implement more than one and maybe strategically make a very small door between one scene and the next to make sure that you can transition on your graphics card from one algorithm to another without your game player noticing, right? Like you have to be really sneaky about how you do this stuff. There's one additional quick topic I thought I'd cover for fun called deep shadow maps. It has not been coupled with deep learning to my knowledge, but give it a year or two, given computer vision community. Essentially, these make really nice shadow maps, but these are going to be for scenes that the complexity is so high that you just don't expect to render them in real time, but you still want to have some cool shadowing effects. And in fact, actually, shadow maps are used in movie production, right? So a lot of times, certain parts of movie images are rasterized rather than ray traced. But of course, there the priority is different. Like if it takes a long time to compute your shadow map, that's fine, because whatever. So a good example of a scene that needs that sort of thing, which I don't think we're equipped to render yet in this course, looks like this. So I have a bunch of pipes and they release steam at the end of the pipe. And of course, steam does produce shadow. It's little droplets of water. But that shadow is like a line integral, which I know is everybody's favorite computation, right? Because essentially what's going on? You have some light bulb, which is like here-ish, shining down through this big cloud of particles. And then the more that light ray intersects with my cloud of particles, the darker it becomes. This is different from everything we've done so far, where your shadows are essentially binary, right? Like you're either lit or you're not. When we talked about soft shadows, the reason it was soft was because the light rays could come from different places, but the light rays themselves either run into something or they didn't like somehow partially decay, which is what's going on in this kind of a scene. And this happens a lot, right? I mean, it happens in fluid simulation. Like in movie pipelines, this is a really critical thing to get right. And even if you're ray tracing, it's not so clear how to handle this. Like the code that you guys wrote in this class won't be able to do it. I think. I didn't look closely at your extra credit. I'd be surprised if one of you guys did this for extra credit. That would be ambitious. Okay, so there's a technique out there. It's called deep shadow maps. And this is for things that are participating media, which is a term for things like smoke, some people's hair, not my own hair. Things that kind of take away light but don't take it away completely. And so this is just going to handle shadowing and not scattering, right? That's another effect that you have to deal with a lot in this kind of scenario. And the basic point here is that your shadow map now has another dimension to it, right? So far, my shadow map is just like this little grid that's sitting in front of my eyeball. Now, what I'm going to do, I'm going to totally ruin this drawing in like t-3 seconds here. I'm going to take this thing and I'm going to extend it to like a little cube sitting in 3D, where now the value I'm going to store is not just am I lit or not, but rather the percentage of the light that goes through this voxel that is remaining when I get to this depth. So in other words, I'm going to put a big giant volume all the way out from my light bulb to the very end of my scene, and what it's going to keep track of is the percentage of light that's left over by the time I get to that point. That make sense? Computationally, is this cheap or expensive? It's extremely expensive. Yeah. So this is something that would be used in like movie production, rather than like your video game has like you're swishing smoke around and it's trying to render a shadow underneath it. That'd be pretty cool if you could pull that off. Right. So this is again, it's like the fraction of occlusion, which of course physically means nothing, by the way, but it's just roughly like the brightness of the light decaying. Due to like small occlusion, semi-transparent stuff, smoke, volumetric effect, and so on. So kind of conceptually, you can think of it like a little plot that starts out at 100%, runs into your participating media, and then starts to decay, right? And so this is the kind of computation you would do offline about your scene. Is it a pre-processing step? Yeah.
How would they decide how much light is being lost? Is that like kind of someone's just like, oh, this looks accurate, or are they like?
It's a good question. Yeah, I mean, there are extremely complex calculations that happen here, right? So it depends on your medium, right? So for certain like kind of cloudy glass, it probably is just a function of distance. Like the more your light ray intersects with the glass, the smaller the percentage. Other times it's exponential decay. I think there's some physical models, but probably what happens in practice is people just kind of make it up. I think especially when you do fluid simulation, that's not the case, where in fluid simulation, what you get out is a density value at every point in space. And there really is a model for light decay. I don't remember what it is, but these are things you can get right. Yeah. It's a good question. Yeah.
On the last slide, it seems like the light intensity falls off even for the area that doesn't have
In which one here?
If you look kind of down the middle of where the camera's pointing, it doesn't touch.
Down the middle of what, like that?
Yeah.
Oh, sure, but that's not the curve that's showing. This is kind of a weird diagram. This curve would correspond to one of these rays, right? So I guess in this case, 1, 2, 3, 4. It would probably be, well, yeah, what am I?
Be like percentage of the rays that make it to the end.
Yeah. There's absolutely right. I'm sorry, I was looking at this wrong. We're thinking of this entire region as one pixel in that map, right? So the pixel is this little volume, so it's actually covering this entire space here. And that's why you're seeing all of these different events. Anytime some fraction of this is running into one of those objects, it's decreasing. Yeah. Sorry, yeah, that's absolutely right. Okay, so in any event, that's the basic point here is that as a pre-processing step, you compute this crazy function at every voxel in this giant grid. And then when you're rendering, it's actually not so hard to light stuff, right? You just read off that lighting value and you're kind of done. There are all kinds of tricks out there, like your shadow map is this giant grid worth of numbers. You probably want to compress it in different ways, and there's nice techniques for that. And especially because this is really a secondary lighting effect, right? Like you don't want to waste a ton of computation on it. But it's pretty convincing. And I think this is one of these rendering problems that's pretty forgiving. Like I think your brain is not so good at performing the radon projection you would need to actually know the precise shadow that you should see here. So as long as you kind of see something blobby that roughly corresponds to the action going on over it, I think you're very unlikely to notice if it's a little bit inaccurate. There's a really critical application, which is curly blonde hair, where self-shadowing actually matters quite a bit. Hair is a really annoying participating medium because, at one scale, it's a bunch of little strands that really do occlude each other, but at the scale where you're actually probably doing your rendering, it's not, right? It's just like one big volumetric blob of semi-transparent stuff. It's my understanding of hair. And so getting that self-shadowing right, a very typical technique might be that you render the individual strands, but in addition to that, you have this volumetric shadow map sitting on top of it, so that you just know roughly when I see that strand, like what color it should be. So here's another vaguely disgusting example where you have a ball of hair. And not only is it shadowing itself, it's also shadowing on the ground. Anti-aliasing this is really just a mess. quite a challenging problem. Another place where this kind of issue occurs is in motion stuff. So if you have an object that's moving really fast, and I want to rasterize it. So far, we don't really know how to do that. But a different way to understand that is that you somehow have a semi-transparent participating medium, which is kind of proportional to the amount of time that your shape spends in the different positions. And so if you do that, then you can get a shadow map, which also has a nice blur, as opposed to otherwise you get whatever this crazy output is here. So in any event, these are techniques that we're not going to implement, but are worth knowing is out there. If you do a smoke simulation final project in this course, you may be stuck implementing this technique, because otherwise you're not going to be able to see it, which is a problem. So anyway, that's all for today. I think we'll start end a little early so you can go home and study for your exams. This reminds me, tomorrow, I think I have to be an hour late to my office hour, so I might shift it back an hour. That's probably fine because nobody ever shows up in the first hour anyway. So anyway, just be on the warning and don't let me forget to make an announcement about that. Cool. All right, so on Thursday, I'll see you all for your exams. Huh, fun. I should write that.